All right, let's dive right into this explainer. Today, we're building a first principles mastery of motion graphs. If you're studying for the Cambridge IGCSE Physics 0625 syllabus, or really any foundational physics course for that matter, this is where everything starts to click. We aren't just going to look at lines on a grid today. We're going to translate those lines into actual physical reality, like how a steeper slope actually means a higher velocity in the real world. By the end of this, you'll have a highly structured way of thinking that not only deepens your understanding, but absolutely secures those top marks on your exams. Here's our roadmap for today. We're going to hit the starter challenge, walk through a 4-step framework, look at some real-world applications, figure out how to avoid those sneaky exam traps, and wrap up with quick recall mastery. Let's get into it. Section 1. The starter challenge. Why motion graphs actually matter. You know, it's so incredibly easy to just open up a physics book, see a graph, and try to literally memorize the shape of the line. But hold on. Before we introduce any formal math or equations, ask yourself this. What physical effect, measurement, or prediction actually depends on understanding motion graphs? Answering this is an absolute game changer because it breaks us free from just rote memorization. Once you can pinpoint the actual physical reality that a graph is trying to communicate, will you instantly become way more capable of reasoning your way through those unfamiliar, really challenging exam questions. Moving on to Section 2, the 4-step framework, taking it from concept to execution. So once we understand that graphs actually matter out in the real world, we need a reliable system to analyze them, right? Think of this as your gateway into the bigger scientific patterns that govern forces in motion. It's a strict logical sequence for tackling literally any physics problem. This 4-step mastery sequence is basically your core engine. Step 1, identify the exact quantity or phenomenon you're looking at. Step 2, clearly state the relationship involved. Step 3, explain the underlying physics, the actual why behind the relationship. And finally, Step 4, connect it to a real observation, experiment, or device. The absolute best exam answers always show this seamless blend. They don't just spit out a fact. They walk the examiner step by step through this exact logical sequence. And this perfectly illustrates how we transition from everyday language to precise physics vocabulary. Look, a graph is completely useless if it's just a pretty drawing. You've got to look at the features of the graph, the slope, the area under the line, the direction, the overall shape, and know exactly what they mean physically. Like, is that steep slope representing a speeding up car? Is the shaded area representing the total distance a train just traveled? Whenever you see a graph, you absolutely must insist on translating its geometry into physical, real-world movement. The crucial takeaway here is this. Always, always insist on cause and effect, rather than just memorizing isolated facts. Whether you're dealing with fields, forces, particles, circuits, or waves, you have got to establish a clear chain of cause and effect. Physics is like this giant interconnected web. When a force is applied, an object accelerates, and boom, the slope of your velocity time graph gets steeper. Cause and effect. Once you start thinking this way, the whole subject stops being a boring memory test and genuinely starts becoming a fascinating logical puzzle. All right, Section 3, Real-World Applications. Let's take this beyond the classroom. Let's see how all this builds into actual physical realities. Because let's be honest here, motion graphs definitely weren't invented just to give you exam anxiety. They are literally the fundamental language of the modern engineered world. We're talking crucial stuff here, designing safe transport networks, engineering vehicle safety mechanisms, planning massive energy systems, and even calculating orbital paths in astronomy. As a physics student, you should always be able to pinpoint at least one of these real situations where motion concepts help us predict outcomes and improve designs. If you can explain exactly why the physics helps an engineer design better car brakes using a deceleration graph, well, then you've completely mastered the concept. Next up, Section 4, Avoiding Exam Traps. Let's talk about how to actually secure your marks. Pay very close attention here, because we're going to look at exactly where students unnecessarily drop marks. You can understand the concepts perfectly, but if you don't structure your answers the right way, you just won't get the credit you deserve. A classic weak answer? That's when a student just drops the correct formula onto the page without bothering to explain the variables. They kind of think the math speaks for itself. Well, spoiler alert, it doesn't. The safest method, the one that absolutely guarantees marks, is a complete, connected progression of logic. Remember our 4 steps? Give the definition, state the relationship, provide the explanation, and tie it to the application. Just throwing down an isolated formula simply won't cut it. But hey, you can instantly upgrade a weak response with a really simple fix. If you catch yourself just blindly quoting a process, you need to fix it right then and there by linking it directly to a physical effect. Or, if you provide a real-world example in your answer, don't just drop it and walk away. You have got to show why the underlying physics actually justifies that link. You are rooting every single claim firmly in physical reality. And honestly, that is exactly what examiners are desperately looking for. Finally, Section 5, Quick Recall Mastery. Time for the final checklist. Let's lock in everything we've learned today so it's instantly accessible when you're sitting in that exam hall under pressure. Here are your 4 go-to revision prompts. Whenever you're studying a new motion graph, ask yourself, 1. What's the core idea? 2. What changes physically out there in the real world? 3. What specific quantity or graph feature actually shows that change? And 4. Where is it used in real life? If you can confidently answer these 4 prompts out loud without peeking at your notes, your foundation is incredibly secure. You'll be ready for pretty much any short answer or structured exam question they can throw your way. I'm going to leave you with this provocative thought. The very next time you see a motion graph, whether you're sitting in class or working through a past paper, ask yourself, can you clearly justify the link between those lines on the page and their real-life physical impact? Ensure you're always looking past the paper and seeing the physics actually moving in the real world. Thanks for hanging out with me for this explainer, and definitely keep exploring the physical world around you.